So for those of you who are watching this remotely, you have missed the morning conversation, which is talking about strange functions from real analysis, iterations of logarithms, what can be done to make things converge or diverge. While I am sorry you did not hear that conversation, it is a great preface for what we're going to do today on singularities and why complex is yet again very different than real analysis. So there are three types of singularities. There are removable, there are poles, and then there are the essential singularities. And the essential singularities is everything else. The list is in order of severity. So when you hear the word removable singularity, the definition is apparent, right? It's a singularity that's not really there. So for example, for removable, I don't think the book actually gives an example because it is so obvious. F of z equals z minus 1 over, say, z squared minus 1. If I give you this function, I can factor the denominator as z minus 1, z plus 1. I am trying to resist the temptation not to cancel the z minus 1s. I can't resist the temptation. I must cancel the z minus 1s. And I have the function 1 over z plus 1. If we didn't have so much material to cover, we could spend 15 minutes arguing philosophically, should we be allowed to do this, blah, 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 blah. It's clear, just cancel the z minus 1s. Now, when you originally look at this function, is this function originally defined at z equals 1? Yes or no? The way it's written, it's not defined technically at z equals 1. Nobody wants to get into an argument as to whether or not this function is defined at z equals 1 initially, because you just cancel the z minus 1s, you get 1 over z plus 1. Let's just take this and move on. So this is a really good idea of what we mean by removable singularity. Remove it. Right? Yes?
Can we just define it in the limit?
So one thing is we could define this in the limit, and the limit would exist. But of course, I could have a function that has a split definition. Where, but if I assume, and this is then, the limit does exist, and I want the function to equal that value. So if we use that, we would then be absolutely fine. Okay, poles. So f has a pole of order n if 1 over f has a 0 of order n. And whenever I write the number n, what do you know about the number n? I'm sorry?
It's big.
No. I mean, if you said capital, I wouldn't be able to yell at you for capital, but it's probably positive. We're not going to talk about a 0 of order 0. All right, so 1, n is greater than 0, and 2. What else about n? Integer. There's one other thing. When I write something like n, there is one other thing I'm assuming about it. Complements 1 nicely. Finite. So n is not infinity. We're not going to talk about a function that vanishes to order infinity when we talk about poles. When we get to essential singularities, sure, absolutely fine to be there. This is all other cases where f blows up. It's a really nice definition. It's whatever's left over. So the classic example is the function f of z is e to the 1 over z. So we were having some arguments, for those of you who are tuning in late, to what do we do for the function z minus 1 over z squared minus 1? Yeah, we can just remove the z minus 1 over z minus 1. We can define it. We can take some kind of limit as z approaches 1. Everything is fine. Over here, how do we define this function at 0? Is there a way to define this function at 0?
Yes, but not a useful way.
Good. I absolutely cannot yell at, there is a way to define this at 0. We can make it whatever we want. But there is no way to define it at 0 to make it continuous. This is not a smart-ass answer. This is a good observation. There is no good definition at 0. No good extension to z equals 0. So here, we should really put in z does not equal 0. In everything else, we could easily fix things, but we cannot fix things here. Let's look at f of z. It's going to be the sum, n goes from 0 to infinity, of 1 over n factorial 1 over z to the n if z does not equal 0. This actually has a Taylor series expansion. Or if you want a Lorentz series expansion, if z does not equal 0, we can actually rewrite this and write it as 1 over z. This does have a series expansion at z equals 0. The problem is it has infinitely many negative powers. So infinitely many negative powers in Taylor expansion at z equals 0. And here, only finitely many powers. Only finitely many negative powers. And here, none. No negative powers. So if you look at it this way, this is a nice classification. Now, we haven't proved that all essential singularities are like this, but this is a good start. So we can either explore this function e to the 1 over z first and then do Riemann's theorem on removable singularities, or Riemann's theorem on removable singularities and then explore. Any preference?
The first one.
Okay, so we'll explore. Do you know what the first one is, or are you just saying the first one?
No, this is the first one.
Okay. No, just checking. First loud voice often works. So let's explore e to the 1 over z. Let's get some intuition as to what this function looks like. So the only place where this function is interesting is as z goes to 0. So let's try to figure out, as z goes to 0, what happens. Well, z equals x plus iy. Let's solve for e to the 1 over z equals w. Let's try to figure out which w we can hit. Are there any w that we have to worry about? If I want to find w, are there any w that I do not expect to be able to solve for z? Zero. No chance if w equals 0. Because whatever I take the exponential to, the magnitude of the exponential function is not going to be 0. The only way the magnitude could be 0 is if I'm putting in something whose real part is minus infinity. I cannot put in something whose real part is minus infinity unless I have 1 over negative 0 or something like that. Not going to happen. So we would have e to the 1 over x plus iy. This is the same if we rationalize the denominator. X minus iy over x squared plus y squared equals w. How should we write w? So we could write it as, I'm going to write it as a capital R e to the I theta, where capital R is e to the little r. This is just going to be a convenient way to write it to make the algebra a little bit easier. You always want to think, what is the best way to tackle the algebra? I've got everything as an exponential here. Why not write everything on this side as an exponential and then just match coordinates? So we get e to the x over x squared plus y squared times e to the minus iy over x squared plus y squared equals e to the r e to the I theta. So we get x over x squared plus y squared has to be little r, and we get minus iy over x squared plus y squared equals what? So I want to match things. So what does this have to equal? Well, I put the good. So it has to be I theta. Anything else? Plus or minus 2 pi n. Because when I exponentiate, if I increase theta by 2 pi, so I guess this should be 2 pi. I'll put the I like this. And so if I increase theta by 2 pi n, I'm not going to change e to the I theta. So now I have two equations in two unknowns. You give me r and theta, and I have to solve for x and y. And it's actually even better. I can give you r theta and n and get a sequence of x's and y's. Now I know I've made a huge deal about how complex analysis reduces everything to algebra. We've now reduced things to algebra again. I don't want to do the algebra. This is why I have a math PhD, so I don't have to do algebra anymore. I'll leave this as an exercise. Do the algebra. Given r, theta, and n, find the points x of r, theta, n, and y of r, theta of n. That will give you a point z of r, theta of n. Do you think this is always going to be solvable? If I give you values of theta and n, do you think you should always be able to solve this? Yes. See, this is why I've snuck it in. So now that we're writing it as e to the r equals 0 is allowed. You see how much nicer this is by writing it as e to the little r, not writing it. Otherwise, I'd have to have like the natural log of r or something like that, which I don't want to do. Do you think this is always solvable for any choice of r, theta, and n? So if r is really large, if x and y are really small numbers, x squared plus y squared is going to be smaller than x. And that will inflate the size of this. So this becomes a really nice exercise to try to see what can you do. All right? And so I will leave this as an exercise and try to get a sense of which values are attainable. The shocking value, the shocking result, all r, theta, n, I think, lead to solutions. Or at least infinitely many. Many n for given I'm pretty sure that is the result. So I'm pretty sure that if you try to do the algebra, there'll be, for a given value of r and theta, there'll be infinitely many n that lead to solutions. So go through, try to do the algebra, try to get a sense of what is going on. This means something really strange is happening near an essential singularity. It means you give me a value, and I can give you a point really close to that essential singularity where my function equals that value. This is incredible behavior. Essentially, you see everything near an essential singularity. Well, do we see everything? We don't see okay, so we see almost everything. Okay. Now, of course, this is just one specific function. Maybe other functions with essential singularities have different behavior. I could replace z maybe with z squared. That probably won't change things that much. So this becomes a very interesting question. What does the behavior of a function look like near an essential singularity? What does the behavior of a function look like near a pole? What does the behavior of a function look like near a removable singularity? And that's the goal for today. The goal for today is to try to figure out how does a function behave near these places. Does a function that's complex, that's holomorphic, except at one of these places where we have one of these singularities, does it behave differently than a real variable function? Okay, so I'm going to leave up the definitions and we'll get to Riemann's theorem. So Right now, I think Cauchy is still in the lead. We should have really kept a scorecard to compare Riemann and Cauchy. You know, it's time for Riemann to get into the game. So we have Riemann's theorem on removable singularities. Let F be holomorphic on an open set omega minus a point z naught, bounded on omega, and then if z naught is a singularity for F, it is removable. If you want to phrase it, you can say if. I'll leave it like that. I'm using the if. So the question is always, what is the weakest set of conditions you can put on? And what are the set of conditions that are useful in practice? So we talked about the example earlier where we factored. I don't want to have to factor general holomorphic functions. This is not going to be tractable. So a condition on, if your function is factorable, well, that might be a nice condition. It's not going to be a practical condition to check. The function being bounded, that's not so bad. That's basically saying I have some control over how badly it's behaving in a certain area. Okay, so let's look at the proof. So let's say here's z naught, here's z. I'm going to do it a little bit more generally than in the book. And I'll take some closed curve gamma. All of our proofs look essentially the same. I take some closed curve gamma, I integrate over places where the function might blow up, and I see what happens. I always want to integrate over regions where the function is holomorphic to reduce integrating over a general curve to integrating over small little disks. So what I will do is we'll draw a small little disk about z, we'll draw a small little disk about z naught. We come in, go around, and come back. And then over here, we come in, go around, and come back. So the two interior sectors cancel, and now we have F is holomorphic over this whole region. Technically, when we proved Cauchy's integral formula, I think we only proved Cauchy's integral formula if we integrated along a circle. We could have integrated along any closed curve containing that point, because we could have always taken a smaller circle inside. If you want to imagine that we're doing this over a circle, by all means imagine it's over a circle. If you want to consider the more general nice curve, consider the more general nice curve. So the integral over gamma plus the integral over this plus the integral over this is equal to 0. Okay? All right, so let me see, am I doing this thing right? So I'm going, actually I think I want these going, clockwise. These are always supposed to go clockwise. And then I come back out the other way. Yes. So now we have the integral over gamma plus the integral over this going the wrong way plus the integral of this going the wrong way is equal to 0. So the integral over gamma is the integral over this plus the integral over this. So 1 over 2 pi I integral over gamma is equal to 1 over 2 pi I integral over, we'll say, circle z naught plus integral over the circle of z. So something is missing. What's missing? I'm pretty sure this is not what's in my notes. Yep, this is definitely not what's in my notes. Something is missing. What is missing? Yeah, the integrand. So I need to put something and I need to choose my integrand. I've got my region, that's half the job, but I have to decide what to integrate. Well, when we're thinking of Cauchy's formula, we want to use a function that's holomorphic. I can put in any holomorphic function and this will be true. What's a good holomorphic function to put in? Somehow I wanted to, get something about my function at z. Any thoughts on a good function? When we use Cauchy's integral formula, what's the function we use for Cauchy's integral formula? We don't just integrate f of z. We do, so the integrand is going to be f of z over zeta minus z. I'm sorry, f of zeta over zeta minus z, sorry. Why did we want to use this? Because we don't like it when we have to evaluate a function at this arbitrary point z. We want to reduce knowledge at the boundary to knowledge in the interior. We want to move all the z dependence down here. This is where we had the geometric series expansion. The whole point is I understand the function 1 over zeta minus z. And I want to deduce everything from the knowledge of that one function. So we put this function in these three places. And again, I just want to highlight why we would think to do this. This is what the Cauchy integral formula is. If the function is holomorphic at z, this is actually going to just equal f of z. Hopefully. And then if it equals f of z, if we then take the limit as z approaches z naught, that'll give us the value at z naught. And that will be a way to continue the function. And this goes back to what you said earlier about, can we just do some kind of limit? Yes, we will do a limit. We'll do a limit as z migrates to z naught. So we have three different integrals we're going to be doing. Let's look at the integral over z naught. So if we look at the integral 1 over 2 pi I, integral over the circle at z naught of f of zeta over zeta minus z d zeta. Now we have to be a little bit careful because we're assuming maybe we have a removable singularity. We're assuming there's some problem at the point z naught. Are we ever evaluating our function at z naught? No, we're evaluating at a circle centered at z naught. Okay, what can we say about zeta minus z? So what can we say about zeta minus z? It's bounded. We can choose the radius of these circles so small that this circle stays away from z. So choose radius so small that zeta minus z is, say, greater than 1 over 2015. Or can we always do that? No. Epsilon over 2015. That we can do. We could always choose it so that zeta minus z can't be too small. There's some separation between zeta naught and z. Choose the circle to be, radius at most 1/4 that. We're going to stay away from this by a significant amount. The denominator is bounded. 1 over the denominator can't be too large. What about the numerator? What about f of zeta? Can f of zeta get too large? No, why not? Yeah, the function's bounded. At some point, we should probably use our assumptions, right? Why are we assuming the function is bounded? Because that's going to lead to a really good condition that we can invoke in practice. By assuming f is bounded, by staying away from this point here, this integrand is bounded. What happens is we shrink the radius of this circle. What happens if we shrink the radius of the circle? You're smiling. Go ahead, give the answer. goes to 0. So that's the whole point, is this is true no matter what radius we take. So in the limit as the radius goes to 0, the contribution from this piece goes to 0. So f of zeta over zeta minus z is bounded. The perimeter of the circle f of the circle centered at z naught is of order, say, 2 pi epsilon. As epsilon goes to 0, bounded by b, contribution will be less than or equal to 2 pi epsilon b, which goes to 0. So in the limit, that piece doesn't matter. And we're left with 1 over 2 pi I, the integral along the curve gamma of f of zeta over zeta minus z equals 1 over 2 pi I, the integral over the circle centered at z of f of zeta over zeta minus z d zeta. It's really good to put in the d zeta so you know what you're integrating with respect to. What does this integral equal? What's this integral equal to? Not 0, but not a bad guess. What does this integral equal? I'm integrating f of zeta over zeta minus z over a circle containing the point z in the interior. What does this equal? If you want, if it's not a theorem of Riemann, it's got to be a theorem of Cauchy. What does Cauchy tell us this equals? I'm sorry? This would just be whose integral formula is this? This is Cauchy's integral formula. It says if you take the function f and integrate f along the boundary of f of zeta over zeta minus z, this just equals, this is not good, you guys got to know this, f of z. This is Cauchy's integral formula. It basically says if you know a holomorphic function on the boundary, you know the holomorphic function in the interior. And if you want to think of it as there's a differential equation, if the function is holomorphic, we have the Cauchy-Riemann equations, the nice balance between our two favorite mathematicians in this course, and it fills in uniquely what goes on in the interior. This has to be f of z, because z does not equal z naught. So because z does not equal z naught, this is fine. And so now we have this nice integral, and that's going to equal f of z. Now, take the limit as z goes to z naught. As z goes to z naught, maybe we have some trouble? Well, no. If you look at this integral is absolutely well behaved as z goes to z naught. We're staying away from z naught. We're on the boundary. The numerator is not changing at all. Limit exists. So we've now found a way to define the function at z naught. F of z naught is just going to be 1 over 2 pi I integral along gamma of f of zeta over zeta minus z d zeta. So this goes back to the idea of take the limit. It's what do we take the limit of? We take the limit using Cauchy's integral formula. We know f of z equals this. We now take the limit as z gets closer and closer to z naught. This is always going to be true, so now we have a definition for f of z naught. And this proves that f is holomorphic, because f is now given by the integral of a function that's holomorphic on the boundary. So this finishes the proof of of Riemann's theorem on removable singularities. Oh, sorry. I just forgot to draw the z naught inside. So we can pass the limit inside without any trouble. F is bounded. This is staying away from 0 because we're on the boundary of our region and z0 is in the interior. The integral of the limit will be the limit of the integral because the absolute value is finite. It's a curve of finite length. So I'm not going to use some kind of strange fractal curve or almost fractal curve that has infinite length as we go along. We are staying away from stuff like this. This is a nice closed curve. And so we can take the limit. So if the function is bounded, the singularity can't be too bad. Okay, this, the proof might be a little bit long, but the result should not be that surprising. Being bounded is a strong assumption. Okay, any questions on the first part? Okay, I want to try to keep these three things left, staying on the board as long as possible. So is it okay to erase the middle part over here? Okay. So we get a nice corollary. So the following corollary is true. F, so let's see, say z0 is an isolated singularity, F holomorphic elsewhere, in an open neighborhood. So whenever you're doing these results, you're always looking at some open neighborhood. We'll have some point. F has an isolated singularity at that point, and away from that point, F is holomorphic. Then f of z goes to infinity as z goes to z dot, if and only if f has a pole at z naught. So this is a nice way to describe what it means to have a pole. If you have a pole, then as you get closer and closer and closer to that point, your function is getting larger and larger and larger in magnitude. So for example, let's consider f of z equals e to the 1 over z. Do you think this is going to get arbitrarily large for all choices of z going to 0? If so, that means it has to have a pole. And since we're using this as the stereotype of the essential singularity, which is everything else, this should not go to infinity in absolute value for all choices of z going to z naught, for all choices of z going to 0. Can someone give me a choice of z where the absolute value does not blow up?
We approach purely imaginary.
Yeah, excellent. When in doubt, try the x-axis, try the y-axis, hope one of those works. So let's take z equals iy, then f of iy is e to the 1 over iy. This is e to the minus I 1 over y. So this is going to be cosine of 1 over y minus I sine of 1 over y. It's bounded. So we found a direction where we can go, and the function stays bounded. Is there a direction we can go where the function will explode? Yeah, what direction should we take? Take the real axis. Take z equals 1 over x, then f of z is e to the 1 over 1 over x. This is e to the x. So if, did I do this right? Wait a minute. No, I'm sorry. It's just z equals x, sorry. Z equals x. Take z equals x, we get e to the 1 over z, so we get e to the x. If x goes to 0 from above, and I dropped the 1 over there, fine, 1 over x. Then get explosion. If you want, take x equals 1 over n, f of 1 over n becomes e to the n. So if we approach along the y-axis, it stays bounded. If we approach along the positive x-axis, it explodes. Okay. Let's now look at the proof of the claim. So we have two directions for the proof. So the first is assume f has a pole. So if we assume f has a pole, this means f of z equals, say, a to the minus n, z minus z naught to the negative n plus dot 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 dot. Or conversely, 1 over f of z. You can, well, I'll do it slowly. F of z is equal to a to the minus n, z minus z naught to the minus n. And you can write it as 1 plus g of z. We just factor out the z minus z naught. Everything else is then going to be walking upwards. So now if we look at what's going on, this over here is holomorphic. So as z gets really close to z naught, this has to be tending to what? It's more than just holomorphic. We've pulled out, the next term is z minus z naught to the negative n plus 1. This is a multiple of z minus z naught. Right? When I pull this out, I'm pulling out the highest term. So since this is a multiple of z minus z naught, as z goes to z naught, this goes to 0. So eventually this is going to be at most a half an absolute value. So this quantity here will be at least 1, so it's going to blow up. So z close z naught at most 1/2 in absolute value. And so we get f of z in absolute value will be greater than or equal to 1/2 a to the minus n 1 over z minus z naught to the n. And this diverges. Goes to infinity. Right? So if we have a pole, well, if we have a pole, we can write our function in the following way. We pull this out, we're left with something that's very nice. Eventually this is going to be at most half an absolute value. So this can't completely cancel. This can't explode and go against this. So again, this is tending towards infinity as z goes to z naught. Think of z as z naught plus 1 over n. Z naught plus 1 over 1,000, 1 over 10,000, 1 over 100,000, 1 over a million. This is looking like 1 over a million to a very high power. This is exploding. The only way to stop the explosion is to multiply it by something that's 0. Well, since g of z can never be more than a half an absolute value if z is really close to z naught, there's no way I can get this factor to be close to 0. So the z minus z naught will dominate. Okay. So this goes, to the case when we have a pole. So now the question is, what about the other thing? Let's assume f of z goes to infinity. Okay. So now we want to go this direction. Assume f of z goes to infinity as z goes to z naught. We want to prove that it has to have a pole. So consider, I think I want to do the function 1 over gz. Yeah, I just want 1 over f. Consider the function 1 over f of z. Is this function well defined near z naught? What's the only danger for this function? When I write something like this down, what's the only thing that makes me scared? 0. Do I have to worry about f being 0 near z naught? So danger if f of z equals 0. Is that possible for z near z naught? No. we're told that it goes to infinity in absolute value. Not possible by assumption. Excellent. So it can't be 0. So what that means is if I'm sufficiently close to z0, my function can't be 0. It's got to be at least epsilon. So that means this function is going to be at most 1 over epsilon. Thus, the absolute value of 1 over f of z will be less than or equal to 1 over epsilon if z is close to z0. Thus, 1 over f of z is bounded and has a removable singularity. Right, there's probably a reason we spent all that time proving Riemann's theorem on removable singularities. We can now use that to remove the singularity. So now what can we deduce from this? So I want to claim f has a 0 of finite order. This function 1 over f is holomorphic. Right? 1 over f, I'll do it this way. So 1 over f is holomorphic. So 1 over f of z equals bn z minus z0 to the n plus dot 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 dot. Because it's holomorphic, holomorphic means analytic. Since it's holomorphic, I can now write it like this. I have a finite n here, so therefore it has a pole. So n is finite, therefore pole of finite order. Okay. Any questions on this part over here? So we get some incredible behavior. So we're never going to see, I think, Casorati again this semester, sadly, but we will see Weierstrass several times. So Casorati-Weierstrass is the following. F is holomorphic on omega, save an essential singularity at z0. Then F is dense in a neighborhood of z0. What this means the following. Here's z0. Take any small set about that. Look at f of that small set. F of that small set is dense in the complex plane. You give me any point in C, say W, and I can find a sequence of points in here converging to z0 such that when I apply f, I converge to W. So you get a sequence of points zk in here, such that when you apply f, you get a sequence of points wk converging to w. It turns out a lot more is true. Have any of you ever seen the TV show Name That Tune? So the way Name That Tune works is two people battle it out to try to guess a song. And they say, I can name that song in 5 notes. Oh yeah, I can name that song in 4 notes. I can name that song in 3 notes. Name that song. And they'll play the first 3 notes of the song, and you'll see if you can name it. We're going to play Name That Function. I give you a function that misses 5 points. Can you name that function? I give you a function that misses 4 points. If I give you a function of a real variable that misses 4 points, can you figure out what that function is? No. Look at functions in the real line 1 over 1 plus x squared. Look at the function sine of x. Look at the function e to the minus x squared. Here's 3 nice bounded functions. If I tell you if I tell you even uncountably many points that they miss, you're up the creek. In complex analysis, if I tell you that you miss 2 values, your function must be constant. This is much stronger than Casorati-Weierstrass. You can go even, I won't say how far you can go. I'll just leave it for now as if you miss 2 points, you must be constant. So what that means is, if I know the value of the function at 1 point, and I know that there are 2 values in the complex plane that are not hit by my function, the only function that works is that constant function. That is absolutely amazing. Okay? Any questions on the statement? Casorati-Weierstrass is much weaker than that. Casorati-Weierstrass, you can still miss a huge number of values. It just says you're dense. It says you give me any point in the complex plane, I can find a sequence of points that converge to it. Much more is true. These lead to what's called the Picard theorems. Okay? There's big Picard, there's little Picard. We might talk a little bit about some of them. Proof of Casorati-Weierstrass. So assume f is not dense. Therefore, there exists a small neighborhood about some w such that nothing inside hit. So if you want, here's my point z0, here's my small neighborhood about z0, here's some point w in the complex plane, here's some neighborhood about w, and when I apply my f to those points, I get a sequence of points that stay outside of this neighborhood. I don't get anything close to w. If I did, it would violate it being dense. So I can't get too close to this point. So consider g of z equals 1 over f of z minus w. Is this well defined? So is this well defined? Yeah. F of z is never equal to w, never divide by 0. No division by 0. So this is well defined. All right, so we can ask what's going on about this. The absolute value of g of z is going to be less than or equal to 1 over r, where r is the radius. Because I have some small disk about w. I'm never within r of it. So this must be at most 1 over r. Ooh, we have a holomorphic function which is bounded in a neighborhood of this point z0. What can we deduce? I'm sorry? It doesn't have to be constant. So what's that theorem? It's a removable singularity. As g is bounded, singularity is removable. If we even have one. Because this function is bounded, so g is holomorphic. So there are 2 cases. Case 1, g of z0 does not equal 0. Case 2, g of z0 equals 0. Well, if g of z0 is not 0, then we get f of z is equal to 1 over g of z plus w is holomorphic. Contradiction. So the only possibility is g is 0. Well, if g is 0, g is holomorphic, which implies g is analytic, which implies 0 of finite order. And that's going to contradict the essential singularity. And this is why the definition of essential singularity is anything that does not have a pole of finite order. All right, so this is a good place to stop. This is, I think, all we're going to be doing on singularities like this. We'll now go back to doing some of the applications of this. These theorems are useful in terms of getting a sense of how functions behave.